In this video, we're going to run through a couple examples of the technique of implicit differentiation. The directions for this will say find dy over dx, and this is the relation that we've been given. Now, one of the big things for implicit differentiation is we're not going to bother trying to solve for solve for y. I don't even care if it's possible. I'm just going to go ahead and differentiate right now with respect to x. Now, as a reminder, we are going to assume that y is a function of x through all of this. So if y shows up in a product or in a composition, we will need to make use of the appropriate rules for that. So starting left to right, the derivative with respect to x of x cubed, this would be simply a power rule problem, and we would get 3x squared minus. For the next term, x times y squared, this would be considered a product of two functions, so I will apply the product rule. So first, times derivative of the second, plus the second times the derivative of the first. Please note the extra use of parentheses. This is because it started with a minus, and that minus is going to distribute through to both of these terms. Plus, for the derivative with respect to x of y cubed, this would be considered a composition of functions where your outside function is the third power, and your inside function would be considered y. So according to the chain rule, we differentiate the third power, which would be 3 times that thing squared, and then multiply by the derivative of the inside. Here's my favorite derivative to take of the entire relation. 1. 0, because that's going to be a constant. All right. So a couple more things to simplify here. We'll leave this inside parentheses for the time being. This is going to be x times. The derivative with respect to x of y squared is going to work very similarly to the derivative that we did back here with the y cubed. First we apply the power rule and call this 2y. Then we multiply by the derivative of the inside function in this case being y. Then the derivative with respect to x of x will simply be 1. At this point, all of my calculus is done, and it's simply a matter of doing a little bit of algebra. So first thing I'm going to do is distribute this minus sign and sort of clean this part up. This will be 3x squared minus 2xy times dy over dx minus, from the negative, y squared plus 3y squared times dy over dx. This is all equal to 0. Once again, at this point the calculus is done. Now it's a matter of doing some algebra. What I'm going to do is gather all of the dy dx terms on one side. I'm going to get all of the other terms over to the other side. So I'm going to leave these two terms on the left-hand side. So negative 2xy times dy over dx plus 3y squared times dy over dx is equal to. I'm going to move this minus y squared over to the right-hand side by adding it to both sides. I'm going to move this 3x squared over to the right-hand side by subtracting it. Next thing I'm going to do is treat dy over dx as though it's a common factor of the two terms on the left-hand side and factor it out, leaving me with negative 2xy plus 3y squared. That's still equal to y squared minus 3x squared. To finish solving for dy dx, this is dy dx times this term, so I'm simply going to divide both sides by that term. So final answer for this dy over dx, found through implicit differentiation, will be y squared minus 3x squared all over negative 2xy plus 3y squared. That'll be our final answer for our implicit differentiation. Now, given that we only used the power rule, the chain rule, and the product rule on this one, I did want to throw in some more rules in another example. So I'd like to have us take a look at the following. In this example, I'd like for us to take a look at the sine of x times y is equal to the cosine of x plus y. It has a really fun looking graph if you wanted to check that out using a piece of graphing software like the software available at desmos.com or Wolfram Alpha. Any of those websites would be just peachy. So with that in mind, we're going to differentiate with respect to x both sides. Start with the left-hand side. This would be considered a composition of functions, with your outermost function being the sine function. So we will take the derivative of the sine function to get the cosine function. Then the chain rule says we'll then multiply by the derivative of what's on the inside of that function. The right-hand side will work very similarly, except the outermost function is the cosine. Its derivative will be the negative sine function. Then, once again, the chain rule says we're going to multiply by the derivative of what was on the inside. Now we're still operating under the same assumption as the last problem, which is that y is some function of x. So anytime we take the derivative of something involving a y, we're going to see a dy over dx pop up. We'll start over here on the left-hand side. When we differentiate x times y, we will need to make use of the product rule for this. So, first times derivative of the second plus the second times the derivative of the first. So derivative of the second was the derivative of y with respect to x, that'll be dy over dx. And the second times derivative of the first, that would be the derivative of x with respect to x, which would simply be 1. Continuing on to the right-hand side, once again differentiating with respect to x, x will simply be 1 plus derivative of y will be dy over dx. At this point, the calculus is officially done, and we are going to take the same approach as what we did on the previous problem. First, we'll apply the distributive property a couple times. On the left-hand side, we will see x times the cosine of xy times dy over dx. That's distributing the cosine of xy to these two factors here, plus y times the cosine of xy. On the right-hand side, we'll distribute the negative sine of x plus y to the 1. We'll get negative sine of x plus y. And distributing to the dy over dx, we will get minus dy over dx times the sine of x plus y. As we did for the previous problem, I would like to gather all of the dy over dx terms on the same side. I'm going to gather them on the left-hand side. So the x times cosine of xy times dy over dx will stay on the left-hand side, and we'll get this term over there by adding it to both sides. So this will be plus dy over dx times the sine of x plus y. Anything that doesn't have a dy over dx, I'd like to gather on the right-hand side. So this term will stay on the right-hand side. So minus sine of x plus y. This term I'll get to the right-hand side by subtracting it from both sides. So y times the cosine of xy. Now with that in mind, on the left-hand side, we're now going to treat that dy dx as though it's a greatest common factor, leaving us with x times the cosine of xy plus the sine of x plus y. The right-hand side will stay the same. Something on the right side of this desk is kind of creaky. I hope it's not too distracting. Now with that in mind, just like we did on the previous problem, we have dy dx times this big massive term, so I'm going to divide both sides by this big massive term. So dy over dx is going to be equal to, big fraction, the right-hand side, negative sine of x plus y, minus y times the cosine of xy. This will all be divided by what we had on the left-hand side. So x times the cosine of xy plus the sine of x plus y. That will be our final answer for our derivative dy over dx.